Right now, people along stretches of the U.S. East Coast are stepping onto porches, opening neighborhood apps, and asking the same stripped-down question with the same stripped-down language. Did you hear that? Not a rumble that fades into rain. Not a truck tailgate slamming 2 streets over. A sharp concussive crack. Sometimes two. Sometimes a rolling sequence spaced far enough apart to feel mechanical, but strange enough to feel wrong. Windows twitch, dogs startle, car alarms occasionally answer back. And in too many cases, there is no visible storm, no confirmed earthquake, no headline large enough to explain what entire neighborhoods insist they just experienced. This is the central thesis of this video, and it matters. These booms are not one thing. They are the collision point between atmosphere, infrastructure, surveillance gaps, public perception, military and industrial activity, sensor limitations, and a baseline environment that is no longer behaving on the old calendar. That is the framework that actually means something, not one mystery, a stack of interacting systems. If this has you hooked, subscribe to the Cosmic Forecast so you do not miss what comes next, because this story is just getting started. And drop a comment below. I want to know where in the world you are watching from, what time it is where you are, and your honest take on the central question. When the sky makes a sound that feels explosive and nobody can immediately explain it, what do you trust first? Your senses, official silence, or the pattern of previous events? Because this is the part that should stop you cold. The East Coast is one of the most instrumented, populated, observed, and surveilled corridors on Earth. It has Doppler radar, lightning detection networks, FAA tracking, USGS seismic systems. In some areas, it has local infrasound research arrays, weather balloons, ship traffic data, military warning areas, marine weather observations, and a population density high enough that almost nothing goes unnoticed for more than a few minutes. And yet people are still hearing booms that remain unresolved. Let me say that again so it registers. Not unresolved because nothing happened. Unresolved because different systems are built to detect different classes of events, and the event people experience as an explosion in the sky may fall between those systems, beneath their thresholds, outside their access rules, or inside a gray zone where the signal exists but attribution does not. That gap is where speculation breeds. It is also where real science begins. When people hear a sudden boom overhead, the instinct is linear. Something exploded. Find the explosion. But atmospheric acoustics are not linear. A sound source may be offshore and heard inland. It may be high altitude and perceived as local. It may be a sonic boom without a visible aircraft, thunder without obvious storm structure, an industrial detonation carried far beyond its normal footprint, or a meteoroid fragmenting tens of kilometers overhead. One cause, many signatures, or one signature, many causes. You live inside a fluid, that fluid bends sound. And over the East Coast, where cold shelves meet warm currents, sea breeze fronts meet urban heat islands, marine layers stack under dry air aloft, and human activity overlays all of it. That fluid can do things most people never think about until the windows rattle. This is not hyperbole. It is boundary layer physics. The explanation is not going to be comforting in the way simple explanations feel comforting. It will be more precise than that. We are going to walk through what is observed, what is likely, what is possible, what is ruled out, and what remains genuinely uncertain. We are going to look at why nobody knows why is only partly true. In many cases, the real answer is not that nobody knows. It is that no single institution sees the whole event from source to perception. That is the gap, and the gap is widening. The first mistake is to assume all reports of sky booms belong to the same category. They do not. A resident in coastal New Jersey hearing a midday double crack under a strong inversion, is not necessarily experiencing the same phenomenon as someone in eastern North Carolina hearing a low rolling blast before dawn, or someone in southern New England reporting one house-jolting bang on a clear winter evening. The human brain groups by sensation, physics groups by mechanism. Those are not the same thing. The East Coast gives you a misleading sense of continuity because the corridor is dense. Reports travel fast. A boom in Delaware is discussed in Philadelphia. A sound heard offshore of the Carolinas enters social media in Virginia within minutes. A meteor over Tennessee becomes heard up and down the coast because the information wave outruns the acoustic one. This is where the information environment starts contaminating the event environment. And here is what makes this so much worse. A boom is one of the least self-identifying signals in environmental perception. If you see a funnel, you think tornado. If you smell smoke, you think fire. If you feel prolonged shaking, you think earthquake. But a loud, impulsive sound has a huge menu of causes: atmospheric, industrial, military, geologic, astronomical, and sometimes structural. A single hard bang is not a diagnosis. It is a symptom. Operationally, agencies sort these by evidence channels. The National Weather Service asks whether there was convection, lightning, or a known atmospheric trigger. The U.S. Geological Survey checks for seismic signatures consistent with quarry blasts, earthquakes, or sonic coupling into the ground. The FAA and Department of Defense look at flight operations, warning areas, temporary flight restrictions, or authorized supersonic activity. NASA's Center for Near-Earth Object Studies, CNEOS, reviews fireball reports and all-sky observations when a bolide is suspected. Local emergency management checks industrial facilities, utilities, and controlled demolition logs. If none of those produce a clean match, the public hears silence and translates silence into concealment. But silence often just means fragmentation. A quarry blast can be fully legal, fully logged, and still sound to the public like a sky explosion, because the sound propagated differently that day. A sonic boom can be heard widely, but not seen on consumer flight apps, because many military aircraft are absent from ADS-B aggregation, delayed on feeds, masked, or operating in warning areas offshore. Thunder can arrive from a storm the listener cannot see, because the storm is beyond the visible horizon, while the acoustic path is favorable. A meteor airburst can be brief, high, and spectacularly efficient at generating sound, without leaving much else a casual observer can confirm. One wave, many faces. Historically, this problem is old. Along the Atlantic coast and near large bodies of water, communities have reported unexplained cannon-like sounds for centuries. Seneca guns in the northeastern United States, Barisal guns in the Ganges Delta, mispoofers along parts of the North Sea coast in Europe. Different names. Same basic human encounter, a sky or horizon boom with no obvious source. The terms sound folkloric because they are old, not because they are imaginary. That distinction matters. The old reports prove people have encountered this class of event for a very long time. The modern reports prove instrumentation still does not flatten the mystery the way people assume it should. If anything, instrumentation makes the mystery more revealing, because when a system misses a real event, you learn something about the system. You also learn something about your own assumptions. Most viewers begin here thinking the question is, what caused the boom? A more serious question is, why do we expect one clean answer from an environment where several independent mechanisms can produce nearly identical human experiences? Once you see that, the frame changes. The boom is the headline. The system behind the boom is the story. And on the cosmic forecast, that is always the story. Let me walk you through the mechanism that most people never heard about, and that explains more of these reports than almost any other single factor: atmospheric ducting and temperature inversion. Sound does not simply spread outward in perfect circles and fade. It moves through a medium whose temperature, density, humidity, and wind structure change with height. Those changes refract sound, bend it, focus it, scatter it, trap it, or let it escape upward. In ordinary daytime mixing, warm ground heats the air near the surface. Convection churns the lower atmosphere, and sound from a distant, impulsive source often disperses and weakens. But during a temperature inversion, that structure flips. Cooler, denser air is trapped near the surface while warmer air sits above it. Instead of sound escaping upward, some frequencies can bend back down. Think of it like shining a flashlight into a hall of angled mirrors rather than into open fog. The beam does not travel the way your intuition expects. It gets redirected. That sounds elegant, and it is, but it is also a confession. It means a loud source you think is a mile away may be 20 miles away, or 50, over water and stable coastal air, sometimes farther. A classic way acousticians describe this is through effective sound speed profiles, not just the thermodynamic speed of sound, but the way wind direction and wind speed aloft modify how waves propagate. At roughly 20 degrees Celsius, sound moves at about 343 meters per second. That is about 1,235 kilometers per hour, or 767 miles per hour. But what matters operationally is not just that baseline speed. It is how layered wind and temperature either steer the energy toward you or away from you. If the wind increases with height in the direction of propagation, or if an inversion sets up the right refractive gradient, the atmosphere can act like a duct. Then distant becomes local. The Journal of the Acoustical Society of America has published for decades on long-range sound propagation under stratified conditions. And the broad result is not in dispute, even when individual events are. Stable layers matter, wind shear matters, humidity matters, surface roughness matters. Over water, the effect can become especially efficient because the marine boundary layer is often smoother and more stable than the convective interior during particular times of day or night. This is why the timing of reports matters. Dusk, night, early morning, post-frontal clear conditions, cool season stable nights, warm air overrunning cold shelf waters, spring marine layers, autumn nights after a sunny day. These are not random details. They are the preconditions. The preconditions are everything. NOAA radiosonde launches from East Coast sites, places like Wallops Island, Sterling, Brookhaven, Charleston, or Morehead City. Depending on the event corridor, can reveal inversions in black and white. A sounding may show a sharp stable layer in the lowest 1 kilometer, sometimes much lower, and that is the kind of structure that can radically change what residents hear. If you are hearing a blast under those conditions, the source map expands. And here is the part most people miss: ducting is selective. It does not make a sound audible everywhere. It creates corridors, pockets, zones of enhancement, and zones of shadow. So one neighborhood reports a house rattling boom, the next town hears nothing, and social media fills with accusations that one side is fabricating. That asymmetry is exactly what you would expect in some ducted environments. Sound is not democratic, it is conditional. There are historical examples of artillery and blasting noise, carrying extraordinary distances under inversion conditions. There are documented cases near coasts where thunder, industrial sounds, and military detonations were heard far inland or along shorelines in ways that seemed impossible to witnesses on the ground. When you hear the same East Coast county report that it sounded like it was right overhead, that description may be sincere and still wrong about location. Human hearing is poor at locating low-frequency, impulsive sounds, especially when reflections and delayed arrivals are involved. So when someone says, "I know what I heard," believe the first half of that sentence. They heard it. The second half, "and therefore I know where it happened and what caused it," is where the physics starts arguing back. If the atmosphere is a lens, the Western Atlantic is a stage. The East Coast is not just land next to water. It is a very particular acoustic geometry, a long continental margin, a sequence of bays and estuaries, urban surfaces, barrier islands, inlets, shipping lanes, offshore military warning areas, and one of the sharpest thermal boundaries on the planet in the form of the Gulf Stream and its nearby shelf waters. Warm water here, colder water there, a marine layer 1 hour, better vertical mixing the next, sea breeze fronts in the afternoon, nocturnal stabilization after sunset. The sound field over that environment is not simple. Consider what happens when warm air moves over cold nearshore waters. The lowest layer can stabilize fast. That matters. Or consider nighttime offshore flow over cooler coastal zones, with a residual layer above and a low-level jet developing. That matters too. A boom generated over water under those circumstances can travel in ways that make inland listeners think the source was directly above them. Sound loves stable pathways, and the East Coast supplies them. The National Weather Service has issued forecast discussions for years describing marine inversions, low cloud decks, sea fog, and stable boundary layers along the Mid-Atlantic and New England coasts. Forecasters use that language because it changes aviation, visibility, thunderstorm evolution, and temperature. But the same structure can also change acoustics. A marine inversion is not just a forecast nuisance. It is a sound guide. Let me put that in a framework that actually means something. Imagine dropping a marble on a flat wooden table. It skitters outward and loses energy. Now imagine placing the marble inside a shallow channel. Suddenly, the path is constrained and the energy stays organized longer. A stable layer is not a rigid tube, but for some acoustic energy, it behaves like a guiding corridor. Offshore operations that would normally seem too distant to notice can become audible inland. This is one reason coastal residents sometimes hear what sound like artillery rounds or explosions on otherwise quiet evenings. It may be actual ordnance disposal, controlled detonations, military training over warning areas, shipboard operations, or construction-related blasts far from public view. Or it may be thunder refracted from offshore convection. The point is not that the ocean creates sound. The point is that the coupled ocean-atmosphere system can preserve and deliver it. Here is the part that should stop you cold. Because the coastline is densely populated, even a relatively limited acoustic corridor can generate a large social signal. 10 people hearing one offshore event can turn into hundreds of posts within minutes, because those 10 are embedded in digitally connected neighborhoods. What the public perceives as a region-wide outbreak of booms may be a region-wide outbreak of reporting layered on top of a smaller number of actual source events. That does not make the reports false. It makes the map tricky. There are also shoreline reflection and resonance effects in urban and suburban construction. Water towers, bridge spans, low-frequency coupling with house frames, and layered reflections off cloud bases or inversions can change how the sound is experienced. One person hears a crack. Another hears a rolling boom. Another says it felt like pressure more than sound. Those are all clues. Different frequencies, different arrivals, different structures responding differently. You are not just hearing the source. You are hearing the path. And over the East Coast, the path is often the biggest part of the story. If you are investigating unexplained booms over the East Coast, and you do not at least seriously examine military aviation and offshore training, You are not doing a real investigation. Full stop. This is not an accusation. It is operational reality. The East Coast hosts or borders major military aviation infrastructure. Naval Air Station Oceana, Marine Corps Air Station Cherry Point, Seymour Johnson, Joint Base Langley Eustis, Dover, Andrews, McGuire, Shaw, Beaufort, and many more. Offshore warning areas and training routes run along portions of the coast. Military aircraft operate in blocks of airspace that civilian passengers never think about, often over water, often at altitudes and positions where public visibility is poor, and sometimes under conditions where consumer tracking apps give an incomplete picture. Now, to be precise, supersonic flight over land in the United States is heavily restricted by federal regulation. FAA rules are clear on that. Sonic booms over populated land are not supposed to be routine. That matters, but two things can still be true at once. First, aircraft can go supersonic over approved offshore areas or in specially managed contexts. Second, sonic boom-like sounds can be generated or perceived inland depending on geometry, altitude, and propagation conditions, especially near coasts. A sonic boom is not a one-time explosion at the aircraft. It is the pressure signature created as an object moves faster than sound, producing a shock wave that trails the object. The boom you hear arrives when that pressure pattern intersects your location. Depending on aircraft altitude, trajectory, atmospheric structure, and your distance from the path, it can sound like a single boom, a double boom, or a rolling concussive event. The classic double boom comes from nose and tail shock components, though complex signatures can blur that. If an aircraft is at 40,000 feet, about 12 kilometers, the sound may arrive well after the aircraft has passed your visual field entirely or never been seen at all. That delay matters because it destroys common intuition. People look up after they hear the boom. The source is already elsewhere. The Department of Defense will sometimes acknowledge training associated with booms after public reporting spikes, and sometimes it will not, either because the event was not theirs, because the operation was not in fact exceptional, or because the information is not immediately releasable. That ambiguity is fertile ground for rumor. There have been multiple incidents in different parts of the United States where communities reported explosions or earthquakes that later traced to military aircraft generating sonic booms. Local agencies initially denied knowledge because they genuinely did not have it yet. That lag is normal, and here is where the false floor appears. Many viewers stop at "it was military" as though that closes the case. It does not. If there was a military source, the next questions are altitude, location, authorization, path geometry, atmospheric conditions, and why the acoustic footprint manifested where it did. That is not trivia. That is the difference between explanation and handwave. There is also another complication. Not every military-related boom is supersonic flight. Training can involve flares, explosives, demolitions, naval gunfire practice in some contexts, or other activities that generate impulsive sound. Most of that is controlled and regulated. But controlled does not mean obvious to the public. Offshore, beyond the visible horizon on a stable night, a controlled event can sound anything but controlled to the person hearing it. So yes, military activity belongs near the top of the list in some East Coast boom investigations, but treating it as a catch-all is lazy. The real standard is evidence, NOTAMs, training area schedules where public radar data were accessible, witness geometry, time synchronization, and atmospheric soundings. Otherwise, you are not solving the puzzle. You are just choosing your favorite suspect. This is where a lot of modern boom investigations go sideways. People open a flight tracking app, see no aircraft overhead, and conclude either nothing airborne was involved or someone is hiding the truth. Neither conclusion follows. ADS-B is useful. It is not omniscient. Automatic dependent surveillance broadcast works because aircraft equipped with proper transponders broadcast their identity, position, altitude, speed, and other information. Aggregator platforms then collect those signals through networks of receivers. That system is powerful for civilian aviation. It is incomplete for military traffic, special operations, some law enforcement flights, and aircraft whose data may be delayed, filtered, or simply not captured by nearby receivers. Offshore coverage can also be uneven depending on altitude and network density. A plane low over water does not present the same tracking geometry as a transcontinental airliner at cruise altitude. Let me say that again so it registers. No aircraft visible on a consumer app is not proof that no aircraft was there. It is proof that you did not see an aircraft on that app. That sounds pedantic. It is not. It is the difference between data and interpretation. There are also geometry problems. A supersonic aircraft offshore can create a boom heard inland, yet the public instinct is to search directly overhead at the time of the sound. Wrong slice of sky, wrong time window, wrong expectation. The sound you experience at 2:14 p.m. may correspond to an aircraft position minutes earlier and tens of miles away, especially if the boom path intersects your location obliquely. Add ducting, and the mental map becomes even less reliable. FAA advisories, notice to air missions, and some military range warnings can help, but they are not turnkey explanations either. Not every operation is publicly obvious in useful detail. Not every training block is active continuously. And even if an alert area was active, that does not automatically mean a boom originated there. Correlation is not causation, but neither is absence on your phone exculpatory. This is where serious investigation starts sounding boring to people who want a fast answer. You need timestamps synchronized across reports. You need geolocated witness statements. You need radar where available. You need weather soundings. You need seismic checks. You need fireball network searches if a bolide is in play. You need to know whether the reported boom was a single impulse, a sequence, a long rumble, or a pressure wave accompanied by visible streaking. These are not details around the edges. They are the core of attribution. There have been instances where residents reported a possible explosion, and local police found nothing on the ground, only for later reporting to reveal likely sonic boom activity from aircraft over adjacent offshore areas. There have also been cases where people assumed aircraft, and the real culprit was quarry blasting, meteor fragmentation, or thunder carried under anomalous conditions. The overlap in human perception is the trap, and here is the part that most people never heard about. Even official systems can disagree because they are optimized for different things. Air traffic surveillance is built to keep aircraft separated. Weather radar is built to detect hydrometeors and some non-meteorological returns, not shock waves. Seismic systems are built to detect ground motion, not airborne sound unless it couples into the surface strongly enough. Lightning networks detect electrical discharges, not every thunder report. There is no single mystery boom detector watching the entire East Coast in real time. People assume there is. There is not. That is why unresolved booms persist in a modern state. Not because physics failed, because institutional sensing is partitioned. A bolide, a bright meteor that fragments explosively in the atmosphere, belongs on this list not as a fringe possibility, but as a serious, if comparatively infrequent, explanation for a subset of events. When a meteoroid enters the atmosphere at tens of kilometers per second, the compression and heating can cause it to ablate, fragment, and in some cases airburst. Those events can produce bright fireballs, long smoke trails, sonic phenomena, delayed booms, and in stronger cases measurable infrasound. The 2013 Chelyabinsk event remains the clearest modern reminder. A 2013 paper in Nature led by Peter Brown and colleagues estimated the airburst energy at roughly 500 kilotons of TNT equivalent. Let that number breathe for a second. That is not 500 tons. That is 500,000 tons. The blast wave shattered glass across a large area and injured well over 1,000 people, mostly from window breakage. Chelyabinsk was an extreme case compared with the sort of East Coast booms we are discussing, but it establishes the principle beyond argument. The sky can generate explosive acoustic events without a bomb, without an aircraft, and without a ground impact. NASA CNEOS maintains fireball reporting tools and event listings because smaller versions happen more often than the public realizes. Many burn up harmlessly. Some are seen and not heard. Some are heard and not clearly seen due to cloud cover, daylight, or observer angle. Some generate delayed booms because the light arrives essentially instantly, while sound arrives later, sometimes minutes later, depending on altitude and distance. If the source fragmented at, say, 30 kilometers altitude, about 6 miles, and the listener is tens of kilometers away horizontally, the delay can be substantial enough that people disconnect the sound from the luminous event entirely. Then the boom seems mysterious. This is where eyewitness testimony becomes tricky. Many people do not look up until after the sound. Some hear a boom with no flash because it occurred in daylight, behind cloud, or outside their line of sight. Others see a streak and hear nothing because the geometry or atmospheric structure steered the sound elsewhere. NASA, the American Meteor Society, and local all-sky camera networks can sometimes resolve these cases if there are enough observations, but not always. Cloud cover destroys optical evidence. Sparse cameras leave gaps. Small airbursts can slip through if they are not energetic enough to trigger a widely recognized sensor footprint. And here is the negative frame that matters. A meteor explanation is not a magic wildcard you can invoke whenever nobody knows. It is testable. You look for fireball reports, satellite detections where available, whether radar oddities such as non-meteorological trails in rare cases, infrasound detections, dashcam video, doorbell camera light signatures, and trajectory consistency across witnesses. If those are absent, the bolide case weakens. Not eliminated, but weakened. Still, it remains real. There have been East Coast and Eastern U.S. fireball events that produced widespread reports of booms, trembling, and alarm. People often describe them as explosions because, from the ground, that is what they are experiencing, an atmospheric fragmentation event coupling into audible and sometimes infrasonic sound. If you have never heard one before, your brain reaches for the nearest category, explosion, but the mechanism is celestial. That is why investigations cannot stop at local infrastructure. Sometimes the source was never local at all. Sometimes a pebble-sized or boulder-sized piece of space debris from the solar system entered the atmosphere above a populated corridor and announced itself with chemistry, plasma, and shock. The sky is busy, busier than intuition allows. People here, we have satellites, radar, and sensors everywhere, and imagine a seamless awareness grid. The real picture is more jagged. Start with weather radar. The NexRad network is extraordinary for precipitation and storm structure. It can detect birds, bats, insects, smoke plumes, debris, and occasionally strange non-meteorological returns. But it is not designed to image acoustic shock waves from every impulsive event. A sonic boom itself is not a clean radar target. A meteor train may or may not produce a detectable signature depending on altitude, density, ionization, geometry, and timing. Offshore low-altitude phenomena can sit in beam gaps or below useful sampling at long range. If you think whether radar should show you the answer every time, you are assigning it a job it was not built to do. Now take lightning detection. The National Lightning Detection Network, Earth Networks, and GOES East's geostationary lightning mapper are powerful systems. But thunder-like sounds without a clearly mapped lightning stroke still occur, because not every acoustic event is thunder. Not every electrical discharge produces the same audible footprint. And line-of-sight or sensitivity constraints can complicate detection. Weak winter convection, elevated discharges, or unusual propagation can all muddy perception. Again, the absence of a neat lightning map match does not close the case. Seismic networks have their own threshold problem. USGS and regional networks can sometimes detect quarry blasts, earthquakes, and even strong sonic coupling from meteors or sonic booms if the atmospheric pressure wave efficiently transfers energy into the ground. But many airborne events will not produce a strong or distinctive seismic signature. No seismic trace does not mean no boom. It means no useful ground motion record at that network sensitivity and geometry. Then there is infrasound. This is the tool many viewers assume exists everywhere. It does not. Infrasound arrays can detect low-frequency atmospheric waves from meteors, explosions, volcanoes, and large bolides over long distances. The Comprehensive Nuclear Test Ban Treaty Organization, the CTBTO, maintains a global infrasound network for treaty monitoring. And scientists have used those stations to study meteor airbursts and atmospheric events. But that network is global and strategic, not a dense public neighborhood sensor net for every East Coast boom. Coverage and access limitations matter. Detection depends on event energy, frequency content, background noise, and path conditions. Same story with satellite observation. Some high-energy bolides are detected by U.S. government sensors and later entered into public databases. Some are not released in detail. Some events are too small. Some are obscured. Some occur under geometries that make immediate public confirmation slow or impossible. And this is before we even talk about data latency. A local resident experiences the boom now. The integrating of radar, seismic, aviation, satellite, and meteor reports happens later. In that time gap, rumor becomes architecture. Here is the part that most people never heard about. A well-instrumented society can still feel sensor poor at street level because the public interface to that instrumentation is fragmented. You can check lightning, you can check flights, you can check earthquake feeds, but you cannot easily fuse all of them with local soundings, military operations context, and infrasound interpretation in 5 minutes from your phone. Agencies can do more than the public can. But even agencies are siloed. This is not a malfunction. It is a system design problem, and the math does not work in favor of immediate certainty. Small, brief, off-axis, or borderline threshold events are precisely the kinds of things that produce strong human reaction and weak institutional closure. That combination is why sky booms are durable mysteries even in the sensor age. The public tends to separate thunder from explosions with too much confidence. Under many conditions, that is fair. Thunder is rolling, textured, diffuse. A blast is sharp. But under other conditions, especially distant thunder, thunder refracted by layered air, thunder from elevated convection, or thunder traveling through stable pathways, that distinction breaks down faster than people realize. A lightning channel heats air to temperatures on the order of 30,000 Kelvin, roughly 5 times hotter than the surface of the sun. That rapid heating causes explosive expansion. Thunder is the acoustic result. In other words, the basic mechanism is already an atmospheric shock process. The difference is geometry, structure, and propagation. Nearby thunder often sounds like a crack followed by a roll, because different parts of the lightning channel are at different distances from you. But if the path is unusual, if the storm is partially hidden, if the channel geometry is compact from your perspective, or if the atmosphere favors a hard arrival, thunder can sound uncannily like an explosion. This matters on the East Coast because offshore convection is common. Elevated winter storms occur. Nocturnal convection can sit beyond the visible horizon, and marine layers can bend sound. You may not see a towering storm from inland if it is over the ocean or obscured by low cloud, especially at night, but you can hear its acoustic output if the path is favorable. National Weather Service forecast discussions occasionally describe isolated convection over the coastal waters or elevated instability above a stable surface layer. That is the kind of setup where the sky can produce sound without giving the visual cues people expect. Dry air below cloud base can suppress rain at the surface. Weak radar returns may not look dramatic, yet a single strong discharge can produce a startling acoustic event. There is also acoustic shadowing and focusing. Some areas get the sound, others do not. A person 3 miles away hears nothing and dismisses the report, but the atmosphere did not distribute the sound uniformly. The wave field was structured. Think of a concert hall. The same orchestra sounds different from different seats because reflections, materials, and geometry shape what arrives at your ears. The atmosphere is a moving concert hall with temperature gradients instead of walls. Now make the orchestra one lightning stroke offshore under a nocturnal inversion. That is the problem. A 2018 paper in the Bulletin of the American Meteorological Society on unusual thunder audibility and atmospheric structure would not surprise any forecaster who has worked coastal zones, even if most residents never encounter the concept formally. Forecast offices live in these subtleties. The public usually does not. So when thunder violates the expected sound profile, people search for machinery, explosions, jets, or something hidden. Sometimes that search is correct. Sometimes the storm was there all along. What you need to rule thunder in or out is not just radar, but the right radar at the right tilt, with the right timing plus total lightning data, satellite cloud-top information, and ideally local soundings. If there was no convection anywhere near the relevant path and no electrical activity, thunder drops down the list. If there was elevated offshore convection under favorable propagation conditions, it climbs. This is the deeper pattern. Each candidate explanation has to be tested against both source evidence and path evidence. The public usually asks only about the source. Physics cares about both. Every time unexplained booms trend in winter, somebody brings up frost quakes, also called cryoseisms. That instinct is not absurd. It is just often badly applied. A cryoseism occurs when water-saturated ground or rock fractures under rapid freezing conditions, producing a sudden release of stress and an explosive sound, sometimes accompanied by localized shaking. These events are real. They have been documented in parts of Canada, the northern United States, and New England under the right circumstances. The U.S. Geological Survey and Environment Canada have both discussed them. They tend to happen when there is a quick temperature plunge, little snow insulation, enough groundwater or surface water infiltration, and the right soil or bedrock structure. But cryoseisms are not catch-all winter booms. They are regionally and meteorologically constrained. If reports are coming from coastal areas with temperatures well above freezing, cryoseisms are not your answer. If the timing follows warm advection over cold water or stable marine conditions, that points elsewhere. If the sound was heard across a broad coastal stretch simultaneously, again, that argues against small, isolated ground fractures. Cryoseisms are local. They do not generally explain widespread synchronized offshore-sounding reports. Where they do fit, the description often includes one or more of the following: a very cold snap after thaw or rain, isolated neighborhood reports rather than broad regional waves, brief shaking, and no supporting evidence for aircraft, thunder, or bolides. Even then, proving cryoseism after the fact is hard, unless conditions line up cleanly and there is some ground evidence or a local seismic signal. Many things can mimic the experience. So cryoseisms belong in the toolkit, but low on the list unless the weather regime strongly supports them. This is a good example of what happens when a real phenomenon becomes internet shorthand. People learn one obscure explanation and then spread it across every unresolved sound report as though acquiring a term equals solving the event. It does not. Naming is not knowing. The same problem occurs with earthquake and sonic boom. These are categories with tests, not vibes. In a rigorous investigation, cryoseism is ruled in by weather, hydrology, geology, and spatial scale. If those do not align, discard it and move on. This matters because false specificity wastes time. Once the public latches onto a label, contradictory evidence gets filtered out. A clear spring marine inversion with offshore training activity becomes probably frost quakes because the term is memorable. That is how noise enters the information system. And here is the broader lesson. The East Coast boom story is full of real phenomena that are individually valid and collectively abused. Sonic booms are real. Cryoseisms are real. Meteors are real. Thunder under inversions is real. Quarry blasts are real. Classified activity exists. Social media amplification exists. The challenge is not choosing which of these phenomena to believe in. The challenge is assigning the right one to the right event. That is a higher standard, and it is the only useful one. Not every sky boom comes from the sky. Quarry blasting, mining operations, construction demolition, utility incidents, industrial pressure releases, and offshore engineering work can all generate sounds that the public interprets as aerial explosions. On the East Coast, quarries and aggregate operations exist closer to populated corridors than many residents realize. Controlled blasts are regulated, often logged, and usually designed to minimize off-site effects. Usually, but usually is not always not noticeable. A quarry blast involves multiple charges, timing delays, burden, spacing, stemming, and blast design intended to fracture rock efficiently. The sound that reaches the public can depend not just on the blast itself, but on atmospheric conditions, topography, and low-frequency propagation. Under certain conditions, especially stable air, the acoustic signature can carry far beyond the normal annoyance radius. The U.S. Bureau of Mines and the Office of Surface Mining have long histories of studying blast overpressure, vibration, and community response, because perception often exceeds expected footprints. Let that number breathe for a second. Air overpressure from blasting is often discussed in pounds per square inch, so small they sound trivial on paper. But those tiny pressure changes can still be audible, rattle structures, and alarm residents. Human perception does not require catastrophic force. It requires a sudden enough impulse. There are also offshore and nearshore construction activities, pile driving, demolition, unexploded ordnance disposal in controlled settings, dredging-related blasting, or other marine engineering events. Some of these are tightly managed, environmentally monitored, and announced within industry channels rather than public channels. A coastal resident may experience only the end product, a dull or sharp boom with no visible source. Then there are accidental industrial events, pressure vessel failures, electrical transformer faults, gas line incidents, structural failures. These usually leave local evidence and emergency response trails, so they are often resolved quickly. But in the first minutes, the sound report alone is indistinguishable from many other causes. What separates industrial sources from atmospheric or astronomical ones is often timing regularity, repetition pattern, seismic coupling, and ground truth. A quarry may blast on a schedule. A demolition has permits. A utility event leaves outages. An industrial accident leaves damage. But if the sound path is long and the source is remote, the listener may still classify it as in the sky. That is not irrational. It is an honest inference from limited sensory data. This is where coordination between agencies matters. Police dispatch logs, fire department runs, state mining regulators, local permit databases, and utility monitoring can all help. But again, no single member of the public can query all of that in real time. So the public fills the delay with narrative, and the narrative almost always points upward. Because the sky is psychologically different. If a source is unseen and the sound feels detached from the ground, people elevate it. But acoustically, a distant ground or offshore source under the right atmospheric conditions can detach from its origin and seem aerial. That is the trap. What your ears call vertical may just be poorly localized horizontal sound. The explanation is complete only when source, path, and perception align. Industrial explanations often get dismissed too quickly because they feel too ordinary for an extraordinary sensation. Yet ordinary sources under rare propagation conditions generate extraordinary experiences. That is not a contradiction. That is acoustics. One reason these events feel so threatening is that people are not merely hearing a sound. They are feeling a structure respond. Low-frequency sound and pressure waves interact with buildings in complicated ways. Window panes flex, drywall joints creak, loose trim clicks, garage doors resonate. Wall cavities behave like crude drums. What arrives at your home is then filtered by the building's own resonant properties. Two houses on the same street can report the same event differently because they are different instruments. Think of a guitar lying on a table. Pluck one string and others may hum in sympathy if their resonant frequencies are close enough. Your house does the same thing, just less musically and more ominously. This matters because a moderate external pressure pulse can feel stronger than it objectively is if your structure emphasizes it. A low-frequency component couples into a large window, and suddenly the event feels like impact. Residents say, "It sounded like something hit the house." Maybe nothing did. Maybe the house became a translator. The U.S. Bureau of Mines Blast Research documented for decades that human annoyance and structural response are related but not identical. You can have a pressure or vibration level below damage threshold that still feels severe to occupants. The same is true for sonic booms. NASA and military studies on community response found that even relatively modest booms can trigger strong reactions depending on background quiet, expectation, time of day, and structure type. Expectation matters more than people realize. If a boom occurs in midday urban noise, it may register as curiosity. If it occurs at 2:11 a.m. in a quiet coastal subdivision, it registers as threat. The physical event may be similar. The human event is not. This is where house shaking becomes both important and misleading. Important, because it tells you the signal had enough low-frequency content or structural coupling to produce a response. Misleading, because people often infer that stronger shaking means a nearby source. Not necessarily. Certain low-frequency waves can travel well and excite structures at distance. A more distant, lower-frequency impulse under favorable conditions may shake a home more noticeably than a nearer, sharper, higher-frequency sound. Again, Your senses are real. Their interpretation needs help. There is also the problem of multiple arrivals. Inversions, reflections off cloud bases, terrain edges, urban canyons, and shoreline geometry can create a sequence where the first impulse is followed by delayed rumbles. That pattern strongly suggests thunder to some people and explosions to others. Both are responding to the temporal structure, but without knowing the path, they are guessing. And here is another false floor. Viewers often think once a source is identified, the story ends. It does not, because the public impact depends on the interaction between source and built environment. Why did one county flood emergency lines while the next barely noticed? Why did some homes report rattling and others did not? The answer may lie less in the origin event and more in the propagation corridor and structural resonance. This is what makes these incidents feel bigger than they sometimes are. The boom does not stop at your ears. It enters your house, and your house answers back. Long before radar, social media, or flight tracking, communities reported horizon booms that sounded like cannon fire. The names vary by region. Seneca guns in parts of New York and the northeastern United States, Barasol guns in what is now Bangladesh, mist poofers in Belgium and the Netherlands, Moodus noises in Connecticut, which blended geology and folklore. These labels are not explanations. They are evidence that the class of experience is old. That matters because it rules out one easy narrative. No, mysterious sky booms are not purely a modern artifact of jets, neighborhood apps, or covert technologies. Some are modern, some are not. The archive is much longer than that. Seneca guns are especially relevant here because they became associated with cannon-like reports heard near bodies of water in the Northeast. Explanations proposed over the years included distant thunder, meteors, seismic activity, surf, gas releases, atmospheric ducting, and human activity. None solved every case. That is the point. The phenomenon name survived precisely because multiple mechanisms likely contributed across different events. A label became a basket, and this is where historical anchoring helps. When a present-day East Coast community hears concussive booms and no immediate answer arrives, the situation feels abnormal. But the historical record suggests something subtler. What is abnormal is our expectation that every event should be instantly attributable. The atmosphere has always hidden things. Distance has always distorted sound. Water has always carried it. What changed is the reporting speed. A 19th century fisherman heard a horizon cannon and told a few people. A 21st century commuter hears a double boom in coastal Virginia, and within 90 seconds there are 600 posts across 5 platforms, each with a stronger implied certainty than the last. The event class is ancient. The amplification layer is new. The literature around these historic booms is full of caution. Some reports were surely misidentified thunder. Some likely involved quarrying or artillery in eras when that was more common. Some may have been small meteors or coastal acoustic phenomena. Some may never be resolved. But the persistence of the pattern across centuries and continents tells us we should be humble before the mechanism map. There is no single master key. A historian would say these reports are culturally sticky because they are dramatic and unresolved. A physicist would say they are sticky because multiple natural and human processes converge on the same perceptual output. Both are right, and here is what should stop you cold. The existence of old, unexplained booms does not make modern reports less serious. It makes them more instructive. It means the Earth system and human system have long produced acoustic events that evade simple categorization. The fact that we still struggle to attribute them in the sensor era reveals where our observational architecture remains thin. The old world had mystery because it lacked instruments. The modern world still has mystery because its instruments are specialized. That is a different kind of vulnerability. We need to talk about the information environment because it is not an afterthought. It is part of the event. Neighborhood apps, local Facebook groups, regional subreddits, and text chains create a rapid witness network that did not exist at this scale even 15 years ago. That has real value. It helps establish timing. It reveals geographic spread. It preserves descriptions before memory shifts. It can surface doorbell camera audio, dashcam visuals, and clustering patterns quickly enough to guide investigation. But it also distorts. Psychologists have long documented what is called the clustering illusion, the tendency to perceive meaningful patterns in sparse or random data. When 10 separate booms occur over 2 weeks from different causes, social media can weave them into one ongoing phenomenon. When one boom occurs and 800 people post about it, the volume of discussion can make a localized event feel region-wide. If someone 70 miles away hears something unrelated 2 hours later, the platforms merge them. The event becomes a narrative object. That does not mean public reporting is useless. Far from it. In many unresolved boom cases, public reports are the first meaningful data set, but those reports need structure, time, location, direction of arrival, number of impulses, visible flash or no flash, weather conditions, window rattle or ground shake, delay relative to any observed streak. Without that, the witness network becomes noise. This is why serious investigators often ask for very specific details that casual readers find tedious. They are trying to separate overlapping phenomena. A bolide boom profile is different from repeated quarry blasting. Thunder has temporal clues. Sonic booms have geometry clues. Offshore detonation events may show clustering along shorelines under stable conditions. Public data can reveal that, if handled carefully, there is another layer. Social media rewards the most totalizing explanation, not the most precise one. The military is doing something. It is a secret weapon. It is earthquakes. It is all meteorites. These are satisfying because they compress uncertainty. The actual answer is often a distribution of causes across events, plus a subset that remain unresolved because the evidence threshold was not met. That explanation travels poorly, but it is usually closer to the truth. And here is where the cosmic forecast has to be blunt. If you have been watching this channel, you already know the most viral explanation is often the least operationally useful. What goes viral is not what best fits the physics. It is what best fits the emotional architecture of uncertainty. Hidden actor, hidden motive, hidden truth. That framing feels coherent. It is also often a way of avoiding the more uncomfortable reality that a highly complex society can produce real, jarring, public-facing events without any single clean dashboard to explain them in real time. Sit with that for a moment. The true explanation is less cinematic and more alarming. Not because something omnipotent is being hidden, but because fragmented systems, partial observability, and changing environmental baselines mean ordinary people can experience something powerful and still get no immediate closure. That is harder to live with than conspiracy, which is exactly why conspiracy spreads faster. This is the point where a lot of scripts either overclaim or retreat. We are not going to do either. No, climate change is not a master explanation for every unexplained boom. That would be sloppy. But yes, the changing baseline climate can alter some of the environmental preconditions that influence boom perception and propagation, marine layers, inversion frequency in certain regimes, offshore thunder seasonality, sea breeze behavior, coastal stability structures, and the background state into which sound travels. You have to hold both truths at once. The East Coast has experienced warming ocean waters, shifting seasonal patterns, marine heatwave episodes, and changes in humidity and precipitation characteristics, documented by NOAA and multiple peer-reviewed studies. Coastal waters that run warmer than their 20th century baseline can influence sea breeze contrasts, fog, low cloud, and lower atmosphere stability depending on season and synoptic pattern. Warmer air also changes the vertical structure in which sound propagates, though not in a simple, one-variable way. Increased moisture changes density and thermodynamics. Stronger or differently timed inversions alter ducting potential. Offshore convection may occur in seasons or hours that feel wrong relative to public expectation. That calendar is becoming unreliable. This is not theory, that is thermodynamics. A 2023 NOAA climate summary for the Northeast and Mid-Atlantic does not tell you why a specific boom happened on a specific Tuesday, but it does establish that the background environment is shifting. The floor has risen, coastal waters are warmer, nighttime minimum temperatures in many locations are warmer, some marine layer behaviors are changing. Severe weather season boundaries are becoming fuzzier. None of that means, therefore, mysterious booms. What it means is the old intuition for what the atmosphere should be doing in a given month is becoming less reliable. And public intuition matters because it drives misclassification. Thunder in February sounds impossible until the radar proves otherwise. A stable marine duct in a season people associate with mixed, noisy air sounds improbable until the sounding shows the inversion. An offshore sound source heard inland on a warm winter night feels unnatural because the old local memory says that is not how nights used to behave, but the baseline is moving. The dice are loaded, not toward one specific boom source, but toward more frequent mismatches between expectation and actual atmospheric structure. If marine inversions or stable nocturnal layers become more common or more intense in certain regimes, sound propagation anomalies may also become more common in those regimes. If offshore convection is fueled in shoulders of the season more often, thunder-like booms without obvious local storms may surprise more people. If the atmosphere becomes more humid and stratified in ways that preserve certain acoustic paths, perception changes. To be responsible, though, we need to say what is not yet established. There is no robust published literature proving a direct trend in mysterious East Coast booms caused by climate change. That claim would exceed the evidence. What the evidence supports is a change in background coastal atmospheric and oceanic conditions that can plausibly alter some of the pathways by which sound is generated, transmitted, and interpreted. That is more careful. It is also more useful, because the key thing that separates serious analysis from slogan is mechanism. If the baseline changes the preconditions, then some categories of unexplained boom reports may become harder to interpret using local memory and easier to misread. That does not solve individual cases. It reframes the uncertainty environment in which those cases occur, and that is exactly where the system story lives. We need to deal with the conspiracy frame directly and respectfully, because dismissing it with a smirk teaches people nothing. A common claim is that unexplained sky booms are caused by secret directed energy systems, weather control arrays like HAARP, hidden domestic weapons tests, or some other centralized technology producing atmospheric shock waves over populated areas. The appeal is obvious. It takes a distributed mystery and assigns it to a single actor. It restores intention where reality offers ambiguity, but the physics do not cooperate. HAARP, for example, is a high-frequency radio research facility in Alaska designed to study the ionosphere. It does not sit over the East Coast. It does not operate as an atmospheric artillery cannon. and it does not have the energy delivery mechanism to create widespread localized explosive booms over distant neighborhoods. Radio frequency interactions with the ionosphere are not the same as producing audible overpressure events in the lower atmosphere over cities and coastal towns. The energy budget, geometry, and medium are wrong. Let me say that again so it registers. To generate a regionally audible blast wave in the lower atmosphere, you need a source mechanism that actually couples energy into the air where the sound is heard, at the right amplitude and frequency. If a hidden system were doing that routinely across the East Coast, you would expect correlated signatures, infrasound detections, collateral instrumentation anomalies, satellite clues, repeated consistent spatial patterns, and far more operational leakage than isolated neighborhood posts. The numbers do not just get worse, they break. The same goes for vague secret weapon claims offered without mechanism. A real shock-producing system would have constraints: platform, altitude, energy source, path, acoustic footprint, byproducts. It would not exist as a free-floating explanation that fits every unresolved boom equally well. That is not how engineering works. Now here is the pivot. Saying the conspiracy explanation fails does not mean the real situation is reassuring. In some ways, it is more serious. The true picture is that we have a densely populated corridor where multiple legitimate sound-generating activities and natural phenomena overlap, where public-facing sensor fusion is weak, where military and industrial operations can be partially opaque for understandable reasons, and where atmospheric conditions can radically alter perception. In other words, confusion is not evidence of a hidden omnipotent actor. It is evidence of a fragmented observational state. That is harder, because it means some events will remain unresolved, not because the answer is too grand to reveal, but because the answer was small, transient, off-axis, poorly sensed, and never captured cleanly enough to prove after the fact. That does not satisfy the human need for closure. But closure is not a law of nature. There is also a democratic problem here. Trust erodes when the public experiences a forceful event, and institutions cannot quickly provide a coherent explanation. Into that vacuum pour opportunists, some profiting from clicks, some from ideology, some from sincere but misplaced pattern-seeking. The result is a second-order hazard, not the boom itself. The boom plus epistemic collapse. That is why careful explanation matters, not to debunk for sport but to defend reality testing. If the public cannot distinguish between what is observed, what is modeled, and what is speculated, then every unresolved acoustic event becomes raw material for informational destabilization. That is not an abstract risk. It is already happening. So what would it take to solve one of these events properly? Not in the comments section, not by intuition, operationally. First, synchronize the timeline. You gather all reports with exact local times, corrected for phone clock drift where possible. A 5-minute timing error can make the difference between a meteor, a sonic boom, and a quarry blast. Then geolocate the reports, not just town names, specific coordinates if available. Map who heard one impulse, who heard two, who felt rattling, and who saw a flash or streak. Then you interrogate the atmosphere. Pull the nearest radiosonde data from NOAA. Look at the surface observations, ceiling, winds, temperature-duping spreads, marine layer presence, and whether an inversion existed in the lowest 1 to 2 kilometers. If there was a stable duct aligned from offshore to inland, your source field shifts seaward. If the boundary layer was deeply mixed and chaotic, long-range low-level ducting becomes less likely. Next, check convection. NEXRAD base reflectivity, higher tilts if needed, GOES East satellite imagery, and lightning data from both ground-based and space-based systems. Was there elevated offshore thunder, an isolated winter cell, a decaying convective line beyond the visual horizon. If yes, thunder remains in play. If no, it drops. Then you interrogate the sky traffic. FAA advisories, NOTAMs, warning areas, military operations areas where relevant, and radar or public flight data with all the caveats we discussed. You look not just overhead, but offshore and along likely boom path geometries. Did a fast mover operate in a corridor consistent with the timing? Was there any official acknowledgement? Any training schedule? Any known test activity? If not, that does not end the inquiry, but it changes the weight. Then you go astronomical. NASA CNEOS, American Meteor Society reports, doorbell and dashboard video searches, all sky camera feeds, local astronomical networks. And in some cases, whether radar for unusual non-meteorological traces if timing warrants. If multiple witnesses saw a fireball minutes before the boom, that is a major clue. If none did under overcast skies, that clue may simply be unavailable. Then the ground side. Quarry and blasting logs, state regulators, demolition permits, utility incidents, industrial alarms, police and fire dispatch, Coast Guard notices for offshore operations, Navy or commercial marine advisories. Did anything controlled occur at the right time? Did any accidental event leave evidence? Finally, you check seismic and infrasound data if accessible. Even a weak signal can help discriminate categories. A local seismic thump without atmospheric corroboration suggests one path. A distant infrasound detection with no ground damage suggests another. Notice what is happening here. Every step peels back one more layer of the same event. Source, path, perception, sensor, human report, institutional record. This is not a detective fantasy. It is multidisciplinary environmental forensics. And here is the hard truth. Even after all of that, some events remain unassigned. Not because science failed. Because evidence decayed too fast, timing was too poor, access was incomplete, or the source sat below decisive thresholds. In science and operations, unresolved is not a void. It is a category with reasons. That is important language. Unresolved does not mean imaginary. Unresolved does not mean conspiracy. Unresolved means the available data did not support attribution at the required level. For a culture trained to expect instant answers, that is an almost intolerable sentence. But it is the honest one, and on the cosmic forecast, honesty about uncertainty is part of the job. Now we zoom out. Why this corridor? Why does the East Coast seem to generate so many reports that sound like the sky itself is cracking? Because the East Coast is a rare compression of all the factors that make acoustic attribution hard. Dense population, complex coastlines, variable marine layers, massive aviation traffic, significant military presence, offshore operating zones, industrial corridors, urban canyons, old housing stock that resonates dramatically, high digital connectivity, and a public primed by recent years to assume that if something feels strange, it may signal systemic instability. That last part matters. You are not hearing booms in a vacuum. You are hearing them in an era of alert saturation, wildfire smoke from another country, storm warnings in odd months, trains derailing, infrastructure aging, satellites re-entering, military tensions rising, social feeds full of half-confirmed claims. In that environment, a single unexplained bang carries more interpretive weight than it would have 20 years ago. The sound enters a nervous system already under load. This is the key thing that separates this event class from old folklore. The physical mechanisms may be ancient, but the cognitive environment is new. The public is simultaneously more informed and more overloaded. You can access Doppler radar from your couch, but you are also exposed to 5 contradictory explanations before your coffee cools. That is not better situational awareness. It is higher resolution confusion. The infrastructure mismatch is real too. Much of the East Coast built environment was not designed around the expectation that the public would be constantly auditing environmental anomalies in real time. Agencies issue products for their own operational needs, not for forensic reconstruction by millions of residents. Forecast discussions, marine advisories, seismic traces, and military notices exist in different ecosystems. The person whose windows just rattled must assemble them manually, if they can assemble them at all. That is the recovery gap in information form. A sound happens in 1 second. Explanation takes hours, sometimes days, sometimes never. In that gap, the ratchet clicks down. Trust declines a little more. Institutions sound absent. Communities self-organize around speculation. Next time, the jump to hidden causes is faster. This is why mysterious booms are not just curiosities. They are stress tests. They test how a modern society handles an event that is viscerally real, technically ambiguous, and socially contagious. They reveal where censor systems fail to meet public expectation. They reveal how quickly uncertainty becomes narrative. They reveal how much of our confidence in modern monitoring rests on the illusion of integration. The illusion matters. Because once you assume someone, somewhere must know everything in real time, every delay starts to feel intentional. But the truth is more fragmented than that. The East Coast is watched by many systems. It is not watched by one mind. And that, more than any individual boom, is the thing to remember. So where does that leave us? It leaves us with a conclusion that is less tidy than a reveal and more durable than a slogan. Massive explosive sounds over the East Coast are not one mystery demanding one answer. They are a symptom produced by overlapping categories of real phenomena: atmospheric ducting, inversions, offshore activity, sonic booms, thunder under unusual propagation conditions, meteoric airbursts, industrial blasting, structural resonance, reporting cascades, and observational blind spots. Some events can be solved with disciplined evidence. Some can be narrowed to a few high-probability causes. Some will remain unresolved because the data chain snapped before attribution could be made. That is the honest landscape. And here is the deeper thesis in its most condensed form. This is not mainly a story about strange sounds. It is a story about what happens when a changing atmosphere, complex infrastructure, specialized sensors, and a hyper-networked public collide in real time. The boom is the point where those systems touch. If you came into this video wanting the comfort of one cause, I understand that. Human beings are not built to enjoy unresolved force. A boom feels like a command to find the source, but the system we live inside is messier than that. The air bends sound, water carries it, jets outrun your eyes, meteors detonate high above cloud. Quarries thump beneath stable nights, houses amplify what they receive, apps multiply reports, agencies see slices. Nobody sees the whole board at once, not in the moment, maybe later. Sometimes never. And here is what makes this story stay open. The baseline environment is changing. The East Coast atmosphere is not running on the old script. Warm coastal waters, altered seasonal expectations, and shifting stability regimes do not create every boom, but they change the stage on which booms are heard. Meanwhile, public trust in delayed explanations is thinner than it used to be, and the information ecosystem rewards certainty over accuracy. That means future skyboom events may become not just more noticeable, but more destabilizing, not because each event is larger, but because the gap between experience and explanation is becoming harder to tolerate. If you have been watching the cosmic forecast, you know this pattern. It is never just the event. It is the system around the event. The drought is not just dry land. The storm is not just wind. The launch is not just a rocket. And the boom is not just a boom. It is the sound of fragmentation, acoustic, institutional, and informational, all arriving at once. So the next time windows rattle somewhere along the Atlantic seaboard and officials say they are investigating, the right response is neither panic nor dismissal. It is a more disciplined kind of attention. What were the atmospheric conditions? Was there offshore convection? Was there military activity in a warning area? Did anyone record a fireball? Did seismic systems register anything? Was the sound single, double, rolling, delayed? Which neighborhoods heard it and which did not? Those are not internet trivia questions. They are the architecture of reality. Because one day a boom will be nothing more than distant thunder caught in a strange path. Another day it will be a quarry under an inversion. Another day it will be a military shockwave crossing from offshore. Another day it may be rock from space breaking apart above the coast. And some days, despite all of our systems, it will be none of those things we can prove before the signal fades and the archive goes cold. That is the open loop. Not whether the East Coast sky can boom. It can, it does, it has for centuries. The real question is whether a society built on specialized sensors, fragmented institutions, and overloaded citizens can learn to understand these events faster than misinformation can weaponize them. We do not know the answer yet, but listen carefully. The sky is still asking the question. To understand why these events stay unresolved, you have to stop treating them as headlines and start treating them as time-evolving systems. So let us build one, not a fantasy, not a conspiracy map. A plausible East Coast acoustic event assembled from the kinds of ingredients we know are real. A stable marine boundary layer, heavy online reporting, incomplete aviation visibility. Offshore operations that may or may not matter, weak or distant convection that confuses the acoustic picture, and a public that experiences the force first and explanation later. Picture a late autumn evening along the mid-Atlantic coast. Sunset is gone. The land has been radiating heat away for hours. Inland mixing is collapsing. Over the shelf waters, the temperature structure is messy in exactly the way forecasters respect, and most viewers never think about. There is a shallow cool layer near the surface in some spots, warmer air above in others, and a low-level wind profile, just organized enough to begin steering sound, rather than letting it dissipate upward. A radiosonde launched that evening from a nearby station would not tell you one simple story. It would tell you a layered one, and layered is the whole problem. At 8:11 p.m., a resident in coastal Delaware hears a hard double boom and feels a brief rattle in the back windows. 10 seconds later, a dog in the next house starts barking. Within 1 minute, 3 posts appear on a neighborhood app. Explosion. Did anyone hear that? Whole house shook. 40 miles away, a listener on the Jersey shore hears something less like a crack and more like a low concussive thump followed by a tail of distant rolling pressure. That person does not post immediately because they assume thunder. Farther south, near the mouth of the Chesapeake, someone hears nothing at all. That spatial asymmetry is not noise around the edges of the event. It is the event. Now imagine what the official systems see in the first 5 minutes. Local emergency dispatch receives calls, but responders have no visible fire, no traffic collision, no structure collapse, no smoke plume, and no utility substation showing an obvious catastrophic fault. Police look for the ordinary ground truth of an extraordinary sound and find none. Local television meteorologists check radar fast. They do not see a bright convective core directly overhead. The public takes that absence as a verdict, but radar has not actually answered the question being asked. Meanwhile, offshore, there may be elevated convection over the coastal waters, not an organized line, not a dramatic supercell, just enough electrically active cloud structure to remain relevant. or there may be none. That uncertainty matters, because thunder under anomalous propagation conditions is one of the easiest explanations to dismiss too quickly, and one of the hardest to recover later if nobody preserved the right data fields. The lightning map on a phone is clean over land. Everyone breathes in the wrong direction, so it was not thunder. That conclusion arrives far faster than the evidence required to support it. At 8:14 p.m., somebody opens a flight tracking app and announces there are no jets overhead. The comment explodes. This is always the pivot point, because now the event is no longer just acoustic. It becomes epistemic. One person claims that absence proves secrecy. Another claims it proves mass hysteria. A third says it was definitely quarry blasting, though they do not know whether any quarry in the relevant radius was active. A fourth insists they saw a flash over the water. A fifth says there was no flash, only pressure. Each witness is reporting a real slice. None is reporting the whole system. Let me put that in a framework that actually means something. If you walked into a dark room where 6 people were touching 6 different parts of a machine, one would describe metal vibration, another warm air, another a clicking relay, another a rotating shaft, another a flashing indicator, and another silence. If each insists they experienced the machine and therefore understood the machine, the disagreement is guaranteed. That is what an unresolved boom is, not pure ignorance, partial contact. At 8:18 p.m., local social media has already widened the event footprint beyond what the acoustic evidence can yet justify. People 70 miles away begin asking whether the boom they heard last week is related. Someone posts video of a completely different sound from another state. A national account repackages the moment into a generic, mysterious East Coast explosions thread. The information field outruns the pressure field by an order of magnitude. That is how modern mystery scales. Now let us slow down and examine what a real analyst would do in the first hour. First, they would time order the witness reports and strip them of emotional certainty. Not because emotion is irrelevant, but because adrenaline distorts sequencing. Did the rattle come before the boom or with it? Was there one impulse or two? Was the dog reaction delayed? Did anyone outdoors hear a different profile than anyone indoors? Were the loudest reports clustered along a narrow corridor perpendicular to the coast, which would hint at ducting, or scattered randomly, which might suggest multiple unrelated events being merged online? Second, they would interrogate the atmosphere itself. Surface observations from coastal stations might show light winds, a temperature dew point spread consistent with nocturnal stabilization, and perhaps a low cloud deck offshore. Forecast discussions from the local NWS office might mention a residual marine layer, weak warm advection aloft, or elevated instability over the coastal waters. None of that proves the cause, but it reshapes the menu of plausible causes. A stable path means distant sources become newly plausible. A mixed turbulent boundary layer would suppress some of that. Third, they would test the airborne hypothesis without romanticizing it. Are there public indications of military operations in offshore warning areas? Any known exercises? Any high-speed traffic passing through relevant geometry? Any aircraft absent from public feeds but present in other accessible records? If not, the case is not closed. It is merely unsolved at that branch. People often mistake the inability to confirm one candidate mechanism for evidence in favor of another. That is not how disciplined attribution works. Fourth, they would test the astronomical branch. Any American Meteor Society reports from the same minute. Any all-sky camera hits, any doorbell camera light pulses, any delayed reports of a fireball seen inland or offshore. A bright bolide can generate a clean narrative when enough observers capture the visual event. A smaller or cloud-obscured fragmenting meteor cannot. The boom survives, the flash disappears, the archive ends up thin. And fifth, they would test the industrial branch, quarry schedules, demolition permits, utility anomalies, port operations, dredging or disposal activity. Not because these explanations are glamorous, but because they are common enough to matter and strange enough under certain atmospheric paths to masquerade as something overhead. By 9:05 p.m., if none of those branches has yielded a clean source, the public has already emotionally decided what happened. That is the dangerous interval. Because once a community collectively settles on "the government knows and is not telling us," later evidence has to fight uphill. But there is an equal and opposite failure too. Some institutions, wary of fueling speculation, default to a posture so thin and cautious that it sounds evasive even when it is simply incomplete. We have no information at this time. True, maybe. But to a resident whose windows moved, that sentence does not sound like honesty. It sounds like absence. This is why risk communication around unexplained booms is so difficult. Agencies are speaking in evidentiary thresholds. The public is speaking in visceral force. Those are different languages. A meteorologist says there was no convective signature sufficient to support thunder over land. A resident hears, "They are denying what I experienced." A military spokesperson says there is no information indicating operations that would explain the report. A viewer hears, "They are choosing words carefully." A seismologist says no earthquake was detected. The public was never asking only about earthquakes. In a fragmented information system, every precise non-answer can feel like a general dodge. And here is the part that should stop you cold. This communication mismatch is not a side effect of the mystery. It is one of the mechanisms that keeps the mystery socially alive. If the first authoritative explanation arrives 6 hours late, the event has already crystallized in memory. The sound gets sharper in recollection. The area of impact gets larger. The certainty gets harder. That is not dishonesty. That is how humans metabolize ambiguity. We sand the edges down and harden the shape. By midnight, imagine that the best working hypothesis is still split 3 ways. There was a stable acoustic pathway from offshore toward the counties with the strongest reports. There may have been elevated maritime convection. There may also have been activity in an offshore warning area, though nothing publicly confirmable yet ties it to the timing. No seismic signature. No confirmed fireball. No industrial accident. The real answer, if you were being honest, would be something like this. One or more impulsive sounds were experienced over a narrow coastal corridor under atmospheric conditions favorable for anomalous sound propagation. But the available data do not yet support a singular attribution. That sentence is scientifically respectable. It is socially doomed because it does not satisfy the emotional demand created by the boom itself. The boom feels singular. The explanation sounds plural. The boom feels immediate. The explanation sounds delayed. The boom feels violent. The explanation sounds procedural. And in that mismatch, the conspiratorial frame gains speed. The public says, "If you cannot tell me what it was, then maybe you are hiding what it was." But the deeper truth is often harsher than secrecy. Sometimes the answer is not hidden. It is broken into pieces across systems that do not naturally assemble themselves before the public imagination takes over. That is the modern East Coast boom problem in miniature. What that miniature also reveals is why public memory of these events becomes so sticky. A boom is pure asymmetry. It enters life uninvited, forces immediate bodily attention, and then vanishes before it can be inspected. A tornado leaves a path. A storm leaves radar. An earthquake leaves instruments and damaged fields. But a transient acoustic event can leave almost nothing except synchronized human alarm. That means the archive is made mostly of testimony. And testimony is both essential and unstable. Consider how quickly witness language hardens. In the first minute, a person writes, "Sounded like an explosion." By the second hour, after reading 200 similar posts, the memory becomes, "It was definitely an explosion overhead." By the next morning, after seeing arguments about jets, meteors, and secret testing, the recollection gains added details that may or may not have been present originally. A flash someone is no longer sure they saw, a direction of arrival they inferred from another account, a sense that the whole region experienced it, even if the actual corridor was narrow. This is not fraud. This is reconstructive memory operating inside a network. Researchers in risk perception and disaster communication have spent years documenting how social amplification works. The first description sets a frame. Repetition strengthens it. Uncertainty invites the most emotionally coherent explanation, not necessarily the most evidentially supported one. That is why the wording used in the first 30 minutes matters so much. Possible explosion lands differently than unconfirmed loud noise. Mysterious boom spreads differently than reports under investigation. The acoustic event and the language event begin diverging almost immediately. The East Coast is especially vulnerable to that divergence because the corridor is dense enough for a single event to feel socially enormous. A narrow band of audibility can cut through several counties containing millions of people. If just 0.1% of those residents post, the digital footprint looks gigantic. The information field makes a corridor look like a continent. This is where the clustering illusion returns, and it deserves more attention than it usually gets. People are exquisitely tuned to detect pattern in sparse data because pattern detection is a survival trait. If 3 booms have occurred in the last month, the public will look for a common cause. Sometimes that instinct is right, but sometimes the 3 booms were 3 different mechanisms sharing one human description: a meteor on Tuesday, offshore thunder under ducting on Friday, quarry blasting under an inversion next week. The human category remains explosion in the sky. The mechanism category does not. That is why journalists, meteorologists, emergency managers, and technically literate viewers have a real responsibility here. Not to shut down curiosity, to discipline it. Curiosity without evidentiary structure becomes theater. Curiosity with structure becomes investigation. Let me make this even more concrete. Suppose the same event we imagined earlier produces 3 clusters of reports. Cluster A, along the immediate coast, describes a double boom with window rattle. Cluster B, slightly inland, describes a single low thud with no visible flash. Cluster C, farther north, reports only seeing online chatter and then retrofitting a sound they heard earlier into the same event. Those clusters are not equally reliable for the same questions. Cluster A may be best for timing and arrival structure. Cluster B may indicate propagation edge behavior. Cluster C may be useful for understanding information spread, not source attribution. In real investigations, treating all reports as equal can be as misleading as ignoring them. There is also a class dimension to this story that rarely gets discussed. Communities with more security cameras, more online activity, more access to local meteorologists, and more civic trust generate cleaner early archives. Communities without those advantages often experience the same force with less recoverable documentation. The result is a skewed observational record. Some booms become real because they were captured and discussed at scale. Others remain private folklore because the instrumentation and social amplification were weaker. Sit with that for a moment. What counts as a verified event is partly a function of social infrastructure. Now layer in institutional caution. A local National Weather Service office, may correctly avoid commenting on possible military sources because that is outside its lane. A base public affairs office may decline to discuss operations until facts are established. Local police may limit themselves to what responders observed on the ground. A state geological office may say there was no seismic event. Every agency stays inside its mandate, which is appropriate. But from the public perspective, the result is a chorus of partial truths that does not add up to a full picture. This is why these events feel like systemic wholes rather than single mysteries. The public is encountering the edges of institutions that were not built to provide integrated acoustic attribution in real time. Weather offices forecast weather. Seismologists track ground motion. Air traffic systems track cooperative aircraft. Astronomers track bright enough fireballs. Military public affairs offices handle releasable information on their own timelines. Nobody is the universal translator for one loud sound over a coastal suburb at 8:11 p.m., and yet the public behaves as though such a translator must exist. That expectation is understandable. It is also outdated. The modern state is often imagined as omniscient because its systems are vast, but vast is not the same as unified. Think of a hospital. It may contain world-class cardiology, radiology, oncology, emergency medicine, and surgery. But if a patient moves through 5 departments in 1 hour, nobody automatically experiences the whole case unless someone deliberately integrates it. The institution is powerful. The integration layer is fragile. That is the East Coast boom problem in bureaucratic form. A 2020 paper in Nature Climate Change by Kai Kornhuber and colleagues was not about mysterious booms at all, but about the way large-scale atmospheric pattern changes alter the persistence and shape of extreme weather. Why mention it here? Because it illustrates the deeper principle that environmental baselines shift, and institutions built around older assumptions often lag in how they interpret compound events. The boom itself may not be climate-caused, but the conditions surrounding it, odd season convection, marine heat anomalies, unusual stability structures, altered public expectations, exist inside a system whose baseline is moving. That moving baseline matters for perception as much as for physics. If people expect thunder in July and hear it in March under a strange marine setup, the sound feels more suspicious. If people have lived through smoke from wildfires thousands of miles away, orange noon skies, flood events outside the old season, and repeated infrastructure failures, they are primed to interpret anomalies as signals of systemic instability. The same boom heard in 1994 and 2026 does not enter the same public mind. In that sense, every unexplained East Coast boom is also a referendum on trust. Do you trust your senses, knowing they localize low-frequency, impulsive sound poorly? Do you trust agencies that may genuinely not know yet? Do you trust the first viral account? Do you trust your prior beliefs about secrecy, military activity, or environmental change? Most people think they are evaluating evidence. Often they are evaluating institutions under stress. And here is the part that makes this more than a curiosity channel topic. In an age of fragmented trust, unresolved physical events are no longer merely scientific puzzles. They are civic stressors. A loud, unexplained boom can be small in energy and large in social consequence if it lands in the right information environment. That is what the conspiracy-minded often understand intuitively, even when they misdiagnose the mechanism. The event is not just acoustic. It is political, psychological, and infrastructural, the moment no one can explain it quickly. The real explanation is less cinematic than secret weapons and more destabilizing than secret weapons, because it suggests something broader. It suggests a society dense with sensors and expertise can still fail to produce a coherent shared reality on demand. Full stop. And if that sounds abstract, return to the porch. Return to the resident in Delaware. The window rattled, the dog barked, the phone lit up. No fire trucks arrived. No one in authority had an immediate answer. The body experienced force. The institutions produced lag. Everything that follows grows from that mismatch. This is how one boom becomes a story, one story becomes a pattern, and one pattern becomes a lens through which the public starts reading the sky itself. There is another reason the East Coast keeps producing these episodes, and it has to do with overlap. Most people assume the relevant mechanisms take turns. They do not. The atmosphere does not politely separate the military from the maritime, the geological from the meteorological, or the industrial from the astronomical. Overlapping source fields are not rare. They are normal. Imagine a winter coastal setup in southern New England. Inland temperatures have dropped rapidly after a wet day. Cryocism conditions exist in a few localized places. Offshore, a weak line of elevated convection rides above a stable marine layer. Farther out, scheduled training is occurring in a warning area. Near the coast, a quarry has a legal daytime blasting window that is already closed, so that branch looks less likely. A resident hears a midnight crack. Another hears a dawn rumble. Social media welds them together. By morning, the public thinks there is one ongoing mystery. In physical reality, there may have been 3 different events. That sounds messy because it is messy. A society trained by clean user interfaces forgets that the real world is not menu-driven. You do not click source type and receive a label. You receive overlapping clues from systems built for purposes other than satisfying your intuition. This is one reason historical analogs matter so much. Take Chelyabinsk again. The world understood that event relatively quickly, not because meteor airbursts are easy to diagnose, but because the energy was large enough, the visual evidence abundant enough, and the sensor footprint broad enough to overwhelm alternative narratives. Dashboard cameras captured the flash, windows shattered, infrasound data existed, satellite and trajectory analysis converged, the evidence stack was thick. Now compare that with a much smaller atmospheric airburst over cloud or ocean on the East Coast. Fewer cameras, less optical confirmation, lower energy, more ambient noise. More competing explanations. The physics may be similar in class and completely different in interpretive outcome. Or take a known sonic boom confusion case. Across the United States, there have been numerous instances in which communities reported explosions, called police, and speculated about earthquakes, only for later confirmation to indicate high-speed military aircraft operating in or near authorized areas. The public did not perceive a jet. They perceived a house-shaking pressure signature. By the time the explanation arrived, the event had already acquired folklore. That delay is not incidental. It is built into the geometry of sonic booms and the geometry of information release. The same goes for inversion-amplified industrial noise. Acoustics literature and field reports are full of episodes in which blasting, artillery practice, or industrial detonations propagated far beyond what residents considered plausible. The public inference in those moments is almost always that the source was closer and stranger than it really was. Here again, the atmosphere creates mystery by redistributing certainty. This is why "I know what an explosion sounds like" is not actually the end of the discussion. Most people do know what certain explosions sound like at certain distances under ordinary conditions. Very few know what quarry overpressure sounds like under a nocturnal inversion, what offshore thunder sounds like after ducting, what a meteor boom sounds like when the visual event was hidden by cloud, or what a sonic boom sounds like after interacting with shoreline geometry and a resonant house frame. Experience is real. Generalization from experience is limited. A forensic approach, then, has to become almost embarrassingly specific. What time to the second? What county? What side of the house rattled? Were birds startled before the sound or after? Did anyone outdoors hear a high-frequency crack before the low-frequency thump? Was there a power outage? Did dogs react across several blocks or only in one structure? Did weather stations show a marine influence? Was there low cloud offshore on GOES East visible imagery? Did the nearest radiosonde show a cap or inversion? Was the sound preceded by visible light, followed by light, or unaccompanied by any optical report? These are the kinds of details that feel microscopic until you realize the mystery is built out of microscopic failures of alignment. And this is where the media environment usually fails the public. Television packages and viral clips like Singularity. They like the phrase, "No one knows why," because it is clean, urgent, and emotionally resonant. But the phrase hides the actual shape of the uncertainty. Often many people know many parts of why. They do not know the whole why quickly enough to narrate it in one sentence. That is a different kind of ignorance, more distributed, more frustrating, more revealing. A National Weather Service forecaster may know immediately that the atmosphere that evening was capable of transporting distant sound. A military range expert may know whether any operations occurred in a relevant offshore box. A seismologist may know there was no meaningful ground event. An acoustics researcher may know the witness pattern is consistent with ducting. A local emergency manager may know no industrial site reported a malfunction. Each one has a piece. The public hears none of it in one place, and so the vacuum feels absolute. The vacuum is rarely absolute. It is fragmented. That distinction matters because it changes how a society should respond. If the real problem were one giant hidden cause, the solution would be exposure. If the real problem is distributed sensing and distributed authority, the solution is integration and communication. Those are not the same politics. They are not even the same imagination. Here is the part most people never heard about. Long before a boom is solved, experts can often rank mechanisms by compatibility, not certainty, compatibility. Stable marine layer plus offshore witness corridor, plus no seismic trace, plus no onshore damage, plus a double boom description. Airborne or offshore impulsive source rises on the list. Bright flash plus delayed boom plus scattered all-sky reports. Bolide rises. Rapid freeze plus hyperlocal reports plus shallow ground snap plus no broader corridor. Cryosism rises. Repeated daytime events on a schedule near aggregate operations under stable air. Blasting rises. This is not fortune-telling. It is Bayesian reasoning in work boots. But Bayesian reasoning is a terrible viral product. It does not satisfy people who want categorical speech. That is why communicators have to be more deliberate than they usually are. Instead of saying cause unknown, the better language is often several explanations are possible, and the leading candidates depend on atmospheric conditions, source evidence, and location patterning that are still being checked. Longer, less elegant, more honest. And honesty in moments of acoustic ambiguity is one of the few tools that actually reduces future mistrust. There is a public health angle here too, though not in the obvious sense. Repeated unexplained concussive sounds affect stress physiology. They interrupt sleep. They condition anticipation. They create a kind of anticipatory vigilance in neighborhoods where residents begin scanning the horizon for recurrence. If official explanations arrive rarely or incompletely, the body learns that startling force may occur without closure. That matters. A boom can be non-destructive in engineering terms and still erosive in human terms. You see versions of this after earthquake swarms, after artillery practice near civilian zones, after repeated transformer failures during heat waves, and after unexplained sounds in communities already primed by disaster. The sound is not just measured in decibels. It is measured in what it does to expectation. The East Coast has become an especially sensitive landscape for that expectation because the region is simultaneously old and overloaded. Old housing stock, old infrastructure, old military geography, old port systems, old industrial corridors, but also overloaded digital communication, overloaded weather volatility, overloaded transportation density, overloaded public attention. When a loud, impulsive event enters that matrix, it does not stay small for long. That is why a single unexplained boom can feel like proof of a broader thesis people already carry around, that the systems are straining, that explanations arrive late, that institutions see less than they claim, that the environment is behaving strangely, that nobody is fully in charge. Sometimes those broader feelings attach themselves to the wrong trigger, but the emotional substrate into which the boom lands is real, and there is one more false floor to clear. Some viewers hear all of this and conclude the solution is simply more sensors, more microphones, more infrasound arrays, more all-sky cameras, more public dashboards. Those would help. They would not solve the deeper problem by themselves. Data abundance without interpretive trust can still collapse into argument. A new sensor record does not automatically create a shared reality if the public already assumes institutions are filtering, delaying, or spinning the result. So the answer is not just instrumentation. It is instrumentation plus translation. It is evidence plus narrative discipline. It is the ability to say, in public with precision, here is what we know, here is what we do not know, here is which mechanisms fit the timing and structure, and here is what data would move a candidate explanation up or down. That kind of communication is not glamorous, but in a system where a boom can become a conspiracy in under 10 minutes, glamorous is not the standard. Operationally useful is the standard. And on that standard, most of us are still behind the event. What would it look like if we actually built the response architecture these events demand? Not a fantasy command center. Something realistic. Start local. The first layer is structured witness intake. Instead of generic 911 overflow and chaotic social posting, communities could have a simple public form activated during unexplained acoustic events. Exact time heard, number of impulses, whether indoors or outdoors, whether windows rattled, whether any flash was seen, direction if known, weather conditions, and whether any local damage or power disruption occurred. Most people can answer those questions, and those answers, gathered early, would preserve the raw material before memory edits it. Second layer, immediate atmospheric context. Weather offices already generate far more information than the public ever sees. Surface plots, radiosondes, marine observations, forecast discussions, satellite imagery, lightning products. A rapid acoustic context bulletin could tell the public whether the atmosphere is currently favorable for long-range sound propagation, whether offshore convection exists, and whether inversion conditions make distant sources more plausible. Notice what that does not do. It does not prematurely claim a cause. It explains the stage. That alone would change public interpretation dramatically. Third layer, source screening. Local emergency management could have standing contact trees for utilities, quarries, port authorities, major industrial facilities, and where appropriate, military liaison channels. Not to demand instant disclosure of everything, to rule obvious branches in or out before rumor colonizes the gap. If a quarry did not blast, that matters. If a transformer bank fault occurred, that matters. If offshore training activity was or was not underway in a relevant window. Even a limited acknowledgement matters. Precision lowers panic faster than vagueness does. Fourth layer, archival synthesis. This is where most real-world investigations fail, not because nobody works hard, but because the work is institutionally discontinuous. By the next day, witness reports are scattered across apps. Meteorological data are in one silo, law enforcement notes in another, media stories in another, and any aviation or military context somewhere else again. A serious archive would preserve the event as one package: time series, map, atmospheric profile, candidate causes, unresolved questions. Even if final attribution remained uncertain, the case would be legible. Why does this matter? Because unresolved does not have to mean unintelligible. A society can live with uncertainty better than it can live with incoherence. Now pull back even farther. The East Coast is not merely a location on a map. It is an acoustic civilization built along estuaries, bays, barrier islands, cliffs, bridges, shipping approaches, military corridors, commuter belts, and dense digital networks. The region has old resonant housing, heavy aviation, layered maritime weather, and a public that is never more than seconds away from amplification. In other words, it is almost designed to transform limited physical events into large informational events. That is not a bug in the coast. It is the operating environment. And this is where the comparison to other environmental signals becomes useful. Think about smoke from distant wildfires. A century ago, many communities would have experienced strange haze and odd light, with limited understanding of where it came from. Now satellite imagery and transport models can show the plume path, but public confusion still erupts when the sky turns unfamiliar. Or think about heat domes, atmospheric rivers, sudden stratospheric warming, or geomagnetic storms. The scientific explanation exists. The public encounter still feels uncanny because the event violates inherited local expectation. The gap between model and lived experience is not unique to booms. Booms are simply one of the most visceral versions of it. They are the percussion section of systemic complexity. And because they are so visceral, they expose something important about modern epistemology. We like to believe that more data solve the old problem of mystery. In reality, more data changed the shape of mystery. The old mystery was absence. The new mystery is abundance without integration. There is almost always some relevant data somewhere. The difficulty lies in stitching it together before social certainty outruns analytical certainty. This is why I keep returning to the phrase collision point. The boom is where atmospheric physics, human infrastructure, institutional specialization, and collective psychology intersect. If you only examine one of those, you will keep missing the event that people actually experienced. Take the psychological component seriously. When a sound arrives from an unseen source, humans default toward agency. Something did that. Someone did that. That inference is deeply rooted. It is not stupidity. It is a fast survival heuristic. Agency detection kept ancestors alive. But in a modern environment full of systems that can generate startling outputs without any villain present, the heuristic becomes overactive. The result is a public that can move from audible anomaly to intentional actor narratives almost instantly. Now take the institutional component seriously. Agencies trained not to overstate evidence often communicate in ways that feel bloodless in the face of vivid public experience. They say what they can defend. The public wants to hear what happened. When those do not align, institutional restraint is misread as strategic opacity. That does not mean restraint is wrong. It means translation is missing. Then take the environmental component seriously. As seasonal norms wobble and background conditions shift, events that once fit the local calendar begin arriving out of place. Offshore thunder in a setup the public associates with cold season quiet. Sharp acoustic propagation on a night people expected to be acoustically dead. An atmospheric profile more supportive of ducting than neighborhood memory would suggest. None of these require apocalyptic framing. They require updated literacy. This is not hyperbole. It is adaptation. The public needs a new mental model for sound in a layered atmosphere, just as it needed new mental models for smoke transport, flash drought, marine heat waves, and rainfall rates that exceed 20th century intuition. You are living inside a more conditional system than local memory prepared you for. That is true whether the source is thunder, aircraft, blasting, or rock from space. And rock from space should not be treated as a throwaway line here. One of the reasons Meteor explanations seem exotic is that people intuitively imagine celestial events as rare, singular, and visually obvious. But the atmosphere intercepts material from space constantly, most of it small and harmless. The transition from harmless streak to audible event is governed by size, speed, composition, entry angle, fragmentation behavior, and the observational luck of cloud cover and human attention. A small bolide over the ocean at night can be physically real, acoustically potent, and socially invisible except for the boom. By the time anyone asks the right astronomical question, the best evidence may already be gone. The same principle applies to thunder. People imagine storms as visible towers with obvious rain shafts and mapped lightning clusters. But elevated offshore convection can produce a very different public experience. If the storm is beyond the horizon, if the low-level layer is stable, if the discharge geometry is favorable, then the sound may arrive more clearly than the storm's visual identity. Once again, the event is real, the path is strange, and the witness is left holding an effect without a visible cause. This pattern repeats because cause and perception are not twins. They are cousins. Sometimes distant cousins. And once you accept that, the whole East Coast boom story becomes less supernatural and more demanding. Not easier, demanding. It asks you to think like an acoustician, a meteorologist, an emergency manager, a communication analyst, and a historian at the same time. That is a lot to ask of any viewer. Which is why the temptation toward one-line answers remains so strong. But one-line answers are exactly what fail here. So let us return to the title one last time. Massive explosions are being heard in the skies over the East Coast, and no one knows why. The first half of that sentence captures the experience. The second half captures the frustration. Neither half is fully false, but together they still hide the most important truth. Many of these events are not unknowable. They are underintegrated. They occur at the seam between what the body knows immediately and what institutions can know only after synthesis. That seam is where modern mystery lies, and it is getting crowded. Because the East Coast is entering an era in which baseline anomalies are more common, public trust is thinner, the digital spread of fear is faster, and infrastructure is old enough to produce its own catalog of strange sounds and failures. That does not mean every boom is more dangerous than past booms. It means every boom is entering a more combustible interpretive environment. If you wanted one sentence to carry out of this entire script, let it be this: the unexplained boom is not just an acoustic event. It is a systems test, a test of atmospheric literacy, a test of institutional coordination, a test of communication under uncertainty, a test of whether a networked public can tolerate provisional answers without collapsing into fiction. Those are high stakes for one loud sound. But that is what the sound touches now. And if you have been watching the cosmic forecast, then you already recognize the larger pattern. The issue is never only the object, not the storm, not the launch, not the flare, not the drought, not the reentry, not the quake. The issue is always the contact zone between the physical event and the human system, trying to interpret it before the next event arrives. That is where consequences multiply. That is where trust fractures. That is where a pressure wave becomes a public story about reality itself. So the next time the East Coast sky delivers a concussive report and the first answers are thin, do not mistake that thinness for proof of a hidden master explanation. Sometimes it is. Often it is not. More often, it is the sound of specialized systems failing to converge before a frightened public fills in the missing links. And that should concern you more than the mythology does. Because mythology is at least honest about being myth. Fragmented reality dressed up as certainty is much harder to detect. There is one last layer we have not fully confronted, and it may be the most important one. Why do these sounds bother people so much more than many objectively larger risks? Because a boom violates the contract of the ordinary sky. Rain, wind, lightning, clouds, aircraft, contrails. Even when severe, they belong to a category the public knows how to narrate. A concussive sky sound with no obvious source does not. It feels like a breach in the interface between daily life and the larger forces above it. That is why the reaction is often disproportionate to the actual energy involved. The event is not measured only by force. It is measured by category violation. The ordinary sky is supposed to behave legibly. When it does not, trust recoils. This is also why children remember these events so vividly. Adults may absorb them into political or scientific frames later, but the original impression is primitive. The house shook, the sound came from nowhere, the grown-ups did not know why. That is not merely startling, it is formative. The environment briefly stopped making sense. Communities carry those moments for years, which is why old, unexplained booms become reference points in local memory. Remember the one in March. Remember the one during the freeze. Remember the one when the bay windows shook. These are not just anecdotes, they are local stress fossils, and every new unresolved boom lands on top of that sediment. This is how folklore forms in a modern setting, not from ignorance alone, but from repeated contact with events that are viscerally real and narratively unstable. Folklore is what communities build when the archive is thin but the memory is strong. In earlier centuries, the names were Seneca guns, Barisal guns, mist poofers. In the age of social platforms, folklore arrives with screenshots, audio clips, geotagged claims, and arguments about what radar should have shown. The format changed. The human need did not. A rigorous viewer has to learn to respect both sides of that equation. Respect the memory because something happened. Respect the uncertainty because perception is not attribution. Too much skepticism insults reality. Too much certainty insults method. The discipline is holding both at once. That is harder than it sounds, especially when the event brushes against existing fear. Along the East Coast, those fears are layered. Military escalation, infrastructure fragility, environmental instability, atmospheric weirdness, governmental opacity, and the general sense that the systems carrying daily life have become more brittle. A sky boom acts like a tuning fork for all of them. Strike the air once, and the whole social structure hums. This is why the real explanation is not comforting even when it is non-conspiratorial. It tells you not that an omnipotent actor orchestrated the moment, but that multiple ordinary systems can interact in ways that exceed intuitive understanding, and then fail to explain themselves quickly to the people most affected. That is a deeper kind of vulnerability. It is not dramatic in the cinematic sense. It is structural. Structural vulnerabilities are always harder to communicate because they do not come with a villain in frame. They come with seams. The seam between atmosphere and hearing. The seam between sensors and access. The seam between expertise and public language. the seam between provisional evidence and emotional demand, the seam between what a system can know and what it can say before it knows enough. Those seams are where unexplained booms live, and they are not closing. If anything, some are widening. As automated alerts multiply, as neighborhoods become more networked, as public patience for ambiguity shrinks, and as environmental baselines continue to drift, the same physical event will generate a larger interpretive shock than it once did. That does not mean mystery itself is increasing linearly. It means the social blast radius of mystery is increasing. That matters for emergency management. It matters for journalism. It matters for local trust. It matters for scientific literacy. And it matters for channels like the Cosmic Forecast, because the job is not merely to tell you that something strange happened. The job is to build a framework sturdy enough that strangeness does not automatically become delusion. Frameworks matter. Without them, every anomaly becomes a referendum on hidden power. With them, anomalies become legible even when they remain unresolved. That is a distinction worth defending. Think back to the phrase, "no one knows why." In common speech, it means there is no answer. In technical reality, it often means something more specific. No answer has yet met the standard of evidence needed to be said with confidence across institutions. That is a much narrower claim. It leaves room for ranked mechanisms, for partial confidence, for contextual interpretation, for disciplined uncertainty. Disciplined uncertainty is not weakness. It is the only honest posture when dealing with transient events that move across multiple sensing domains. The problem is that disciplined uncertainty sounds weak in a media economy built to reward hard edges. Probably offshore thunder under favorable propagation with incomplete supporting data loses the click war to mysterious explosion no one can explain. Likely acoustic ducting from a distant impulsive source loses to what are they hiding? But reality is indifferent to what wins the click war. Reality keeps operating on its own terms. And its own terms are conditional. That word should stay with you. Conditional. The East Coast acoustic environment is conditional. Witness reliability is conditional. Sensor visibility is conditional. Public trust is conditional. Baseline expectation is conditional. Even the meaning of a boom is conditional until source, path, and perception are brought into alignment. That alignment is difficult, sometimes impossible after the fact. Which leads to the final open question, the only one worth ending on. Not whether future booms will occur. They will. Not whether some will remain unresolved. They will. The real question is whether communities, institutions, and communicators can build a shared method for living with high-impact uncertainty, without surrendering either to panic or to myth. Can local knowledge, atmospheric science, sensor data, and honest public language be fused quickly enough that the next unexplained boom produces investigation, instead of instant epistemic fracture? Can a society trained to expect immediate answers relearn how to think in probabilities, mechanisms, and incomplete evidence? Can it do that while the environmental stage itself keeps shifting? We do not know, and that ignorance is not empty. It points to work that still has to be done. Better acoustic literacy, better integrated archives, better public explanation. Better humility about what instruments do and do not capture. Better discipline in how we talk about anomaly. Better patience with provisional truth. Those sound like soft tools. They are not. In a world where one unexplained sound can ricochet through millions of people before the first credible explanation is assembled, those are hard infrastructure. Cognitive infrastructure. Civic infrastructure. Interpretive infrastructure. Without them, the next boom will not merely shake windows. It will shake whatever remains of a shared reality. With them, maybe not every event gets solved, but more events stay inside the boundaries of reason. That is not a small difference. That is the difference between a society that can absorb uncertainty and one that turns every acoustic shock into a crisis of meaning. And out over the East Coast tonight, over the shelf waters, over the shipping lanes, over the warning areas, over the barrier islands, over the old mill towns, the ports, the suburbs, the marshes, the bridges, the convective towers hidden beyond the horizon, the low clouds, the aircraft corridors, the quiet neighborhoods where one hard sound can still send people to their windows. The atmosphere is doing what it has always done. It is carrying energy according to physics, not intuition. It is bending paths, building shadows, opening ducts, hiding distance, rearranging certainty. You live inside that system. You always have. The difference now is that the system is louder in the social sense, more interconnected in the informational sense, and less forgiving in the trust sense. So listen carefully the next time a boom rolls through the coast and no answer arrives on schedule. Do not ask only, "What was that?" Ask, "What conditions made it audible? What systems were able to see it? What systems were not? What got merged in the public imagination that may not belong together? What evidence would actually move us from sensation to explanation? And who, exactly, is responsible for translating that journey before the mythology machine gets there first?" That is the question beneath the question. And until we answer it, the sky will keep sounding stranger than it really is. And the system beneath it will keep revealing just how unprepared we are for mysteries that are real, physical, and only partly hidden. One final point before we close. When people hear an unexplained boom, they often believe the central conflict is between believers and skeptics, between the person who says something happened and the person who says calm down. But that is not the real conflict. The real conflict is between two incomplete ways of knowing. One is sensory and immediate. The other is institutional and delayed. One arrives as adrenaline. The other arrives as process. One says the force was real because the windows moved. The other says the explanation must earn its way into the record. Both contain truth. Neither is sufficient alone. That is why these events feel so unresolved even when the physics behind them are not magical. We are trying to join two clocks that do not run at the same speed. The body knows now. Science knows later. Bureaucracy knows later than science. Public memory hardens before all of them finish comparing notes. Once that sequence becomes familiar, every new boom inherits the distrust left behind by the last one. This is the ratchet. It clicks in one direction unless someone does the slow work of rebuilding confidence between event and explanation. And confidence is not rebuilt by pretending certainty exists where it does not. It is rebuilt by showing people the ladder of reasoning. Here were the atmospheric conditions. Here were the candidate mechanisms. Here is why one source rose on the list and another fell. Here is what the sensors did capture. Here is what they were never designed to capture. Here is what remains open. That form of public reasoning is less satisfying than a reveal, but more durable than a slogan. It also respects the audience. On the cosmic forecast, that matters. Because viewers do not need to be sheltered from complexity. They need complexity translated with discipline. If the atmosphere ducted the sound, say so and explain how. If offshore thunder under a stable layer is the leading explanation, say so and explain why that can sound explosive. If a meteor remains possible but unconfirmed, say exactly what evidence is missing. If the military branch cannot be ruled in or out from public data, say that too. Honest uncertainty builds more trust than theatrical certainty ever will. And if institutions want the public to resist bad narratives, they have to offer better ones quickly enough to matter. Not propaganda, not polished reassurance. Better frameworks, better context, better sequencing, better acknowledgement that a forceful, unexplained event can be both real and temporarily unattributed. Communities can handle that truth if it is spoken clearly enough. What they cannot handle indefinitely is the widening gap between what they experience and what anyone seems able to explain. That gap is where mythology, resentment, and opportunism move in. So yes, the East Coast will boom again. Some future event will turn out to be offshore thunder. Another will trace back to a distant industrial source under a favorable inversion. Another may be military. Another may come from space. Another may fade into the archive unresolved. But the larger issue will remain the same: whether the systems around the event are mature enough to keep ambiguity from becoming unreality. That is the standard, not perfect explanation every time. Operational honesty in time to protect a shared sense of what is real. And until that standard is met, every unexplained boom will keep doing double damage. First, the pressure wave hits the house. Then the information wave hits the public mind. The second wave is the one that lasts longest. There is no glamorous ending to that. No final reveal where all the dots lock into place and the sky becomes obedient again. The honest ending is procedural. Build better archives. Preserve first reports before they are contaminated by repetition. Teach people what inversions do. Teach them why lightning maps, flight apps, seismic feeds, and whether radar each answer different questions. Create regional habits of saying, "This is the leading mechanism under current evidence," instead of "case closed" or "nobody knows." That is how a public becomes harder to manipulate without becoming numb, because numbness is not resilience. Resilience is the ability to remain curious without becoming gullible, skeptical without becoming cynical, and provisional without becoming paralyzed. That is a difficult civic skill. It takes practice. It takes communicators who refuse the easy dopamine of certainty. It takes institutions willing to explain not only conclusions but methods. And it takes audiences willing to sit with a sentence that modern life trains them to hate: "We are still checking." Sometimes that sentence is the most responsible one available. Sometimes it is the only wall standing between disciplined reality and a runaway myth. So when the next report spreads across the coast, remember that the first battle is not over what frightened people heard. It is over whether the explanation culture around the event is strong enough to keep pace with the emotion culture around the event. If it is not, the loudest story wins, not the best one. Not the truest one, the loudest one. And in a system already full of stress, that may be the most dangerous boom of all, the one that does not move through the air, but through the network, turning a difficult event into a permanent distortion. That is the open challenge over the East Coast now. Not merely detecting the next sound, but defending the chain of reasoning that keeps sound from becoming superstition, performance, or weaponized confusion. Solve that, and even the unsolved events become smaller. Fail, and every unexplained boom keeps widening into something much harder to contain. That is where the next real test will arrive.